Imagine if the entire ocean was just a giant bowl of soup, but instead of chicken broth, it was seasoned with enough salt to cover every continent in a layer 500 feet deep. It sounds like a fairy tale, but it is the literal reality of our planet. The ocean is salty. We take it for granted. But have you ever wondered where those trillions of tons of salt actually come from? It isn't a giant underwater shaker. It isn't a massive shipwreck of ancient potato chips. The answer starts on land. Rain is not just pure water. As it falls through the atmosphere, it picks up carbon dioxide. This turns the rain slightly acidic. When this acidic rain hits rocks on land, it triggers a process called chemical weathering. The acid breaks down the rocks, releasing mineral ions. These ions are the building blocks of salt. They are carried by rivers and streams into the ocean. This process has been happening for billions of years. Think of it as a constant, slow-motion seasoning of the world's basins. But that is only half of the story. If rivers are the delivery trucks, then underwater volcanoes are the heavy-duty suppliers. Beneath the surface, the ocean floor is alive. Tectonic plates are shifting. Magma rises through cracks in the crust. This is known as hydrothermal activity. As seawater seeps into these cracks, it gets superheated by the magma. It leaches minerals out of the rocks, like water steeping in a giant teabag of volcanic crust. When this hot, mineral-rich water shoots back out into the ocean, it dumps massive amounts of dissolved solids into the mix. So, we have rivers bringing the salts and volcanoes pumping in the rest. But if salt is constantly being added, why doesn't the ocean keep getting saltier until it turns into a solid block of crystal? The ocean has a sophisticated filtration system. It is a biological and chemical balancing act. First, consider the creatures. Coral, clams, and microscopic plankton love salt. Specifically, they crave calcium and silica. They pull these minerals directly out of the water to build their shells and skeletons. When they die, they sink to the bottom, locking those minerals into the sediment of the sea floor for millions of years. Second, there is the clay factor. Certain types of clay minerals settle at the bottom of the ocean. They are essentially sticky sponges for dissolved ions. They trap salt components and bury them under layers of silt. Third, evaporation plays a massive role. When water evaporates to form clouds, it leaves the salt behind. This creates hypersaline environments in shallow areas. Eventually, this salt crystallizes into deposits that are buried by geological movement, removing them from the cycle. The ocean is in a steady state. The amount of salt entering the system roughly equals the amount leaving it. This is why the salinity of the ocean, around 35 parts per thousand, has remained remarkably stable for the last several million years. But let's talk numbers. If you could somehow evaporate all the water in the world's oceans, you would be left with roughly 50 quadrillion tons of salt. That is a 50 followed by 15 zeros. If you spread that salt evenly over the entire surface of the Earth, it would form a layer about 150 meters thick. That is roughly the height of a 40-story skyscraper. Why does this matter? Because the salt content dictates the density of the water. Salt water is heavier than fresh water. This density difference is the engine of the global conveyor belt. The ocean's circulation, the thermohaline circulation, moves heat around the planet. Cold, salty water at the poles sinks to the depths because it is heavy. This creates a massive, global-scale current that carries warmth from the tropics to the shivering coasts of Europe and North America. Without this salt-driven pump, our climate would be unrecognizable. The tropics would be unbearably hot, and the northern latitudes would be frozen wastelands. We owe our current habitable weather patterns to the salt in the sea. Interestingly, not all oceans are created equal. The Dead Sea, for example, is famous for its buoyancy. It is nearly 10 times saltier than the average ocean. Because it is a landlocked basin with no outlet, evaporation is the only way for water to leave. The minerals stay behind, concentrating over time until you can float on the surface like a cork. On the flip side, look at the Baltic Sea. It is incredibly fresh. It is surrounded by land and fed by many rivers, but it has very limited connection to the saltier North Sea. It is a diluted pocket in a global ocean. So, when you take a swim this summer and accidentally swallow a mouthful of seawater, don't just taste the sting. Taste the history of the Earth. You are tasting the chemical weathering of mountain ranges that stood long before humans existed. You are tasting the volcanic fury of the deep crust. You are tasting the geological machinery that keeps our planet's temperature in a perfect, life-sustaining range. We often look at the ocean as a static backdrop to our lives. But it is an active, churning, self-regulating chemistry lab. It is a perfect closed loop. The salt isn't just an additive. It is the fuel for the current. It is the architect of the climate. As we look toward a future of changing temperatures and melting glaciers, we have to remember the balance. When glaciers melt, they dump vast amounts of fresh water into the sea. That fresh water is lighter. It resists sinking. If we pour enough of it into the North Atlantic, we risk slowing down the conveyor belt. We risk disrupting the very engine that has kept our climate stable for millennia. The salt tells a story of millions of years of stability. It is a story of mountains rising, rivers flowing, and volcanoes erupting. It is a story of balance. And as we continue to alter the composition of our planet, we are playing with the dial of that balance. The ocean is salty because the Earth is alive. It is a planet that is constantly recycling its own crust, filtering its own chemistry, and circulating its own heat. The sea is the record keeper of our world's geological journey. Next time you stand on the shore and look out at that endless horizon, don't just see the water. See the chemistry that makes your existence possible. And ask yourself, how much longer can we tip the scales before the balance finally shifts for good?